Okay, can I continue?
Yes.
Okay, similarly, deceleration will be represented this way. So this will be deceleration. So this one is like it's faster at this point, and all of a sudden the steepness of the line is coming down. So it becomes slower. So let me maybe use a different thing to illustrate what I mean. Okay, so if I'm to use straight lines, then this is going to be like from this side to this side. There's the stiffness, and from this
Mm.
side to this side, there's the stiffness. If I'm to use straight line, so you can see that this side from this end to this end is faster, and this side to this side is slower. Are you getting me?
Yes.
So the more the time goes, the more the particle gets slow or it slows down. So this represents deceleration. There is a change in speed, all right, but the change is slowing down the particle. But with the acceleration, you can see that the first instance it will be slower, but the next instance it will be faster
Mm.
because the particle is accelerating. So the acceleration is represented using this curve, and acceleration is represented using the other curve. It's okay.
Yes, please.
Good. So this more or less like a summary. Or before we even go to the summary, let's try to describe the graph.
Okay.
Let's try to describe the graph. Okay, so from between 0 to 20 seconds, what do you think is going on?
There was a constant speed.
There was a constant speed. Can you give me the actual constant speed?
Um, a constant speed of. Come, sorry.
Okay.
Oh, yeah, of 3 meters per second.
Okay, 3 meters per second. There was a constant speed of 3 meters per second.
Yeah.
Between 20 to 40, what can you tell me?
The particle was at rest.
Okay. And now from 40 to 80 seconds, what can you tell me?
The particle accelerated.
Good acceleration. From 80 to 100.
Okay. The particle moved. I'm coming.
There's a line with negative gradient. There is also constant velocity. This
Yeah,
line represents.
I was calculating for it. That's why.
Okay, okay.
Mm.
Okay. So do that calculation for me.
That's It was moving at a constant velocity of -3 meters per
Okay.
second.
Negative 3 meters per second. It was moving with a constant velocity of negative 3 meters per second. Or it can tell me that it was moving with speed 3 meters per second in the opposite direction.
Direction. Okay.
So either ways work. Okay,
Okay.
between 100 and 140, what can you tell me?
It's decelerated.
Okay, deceleration. And later I'll teach you how to calculate the deceleration and acceleration.
Mm.
So when you're talking, you also talk with the numbers.
Mm.
Um, between 140 and 160.
It moved at a constant velocity of -2.25 meters per second.
Okay, okay. And what's happened to the displacement as well? What's happened to what was the particle behind its starting point or in front of the starting point?
It went behind its starting point
With how many units?
with 25 units.
With 25 units. So that is how to describe graph. Once you can describe graph, then you can move between graphs. You see what I just did? the
Yes.
at velocity. So if you are converting a distance time graph or a displacement time graph to a velocity time graph, it becomes very, very easy. But if you can't tell what the lines mean in the graph we are looking at, then it's going to be very difficult to convert that graph into another graph. Is that okay?
Yes, please.
Good. So that is the end of the displacement time graph. We're going to solve questions on this, but only when we are done with the velocity time graph. I'm going to merge them. That is, if you're doing moving between graphs, just like I was talking about. So
Yeah.
this kind of, I can tell you to draw a velocity time graph out of this graph, just like that. So looking at this graph, you draw a velocity time graph. It's a little bit interesting. Yeah. Now there's a summary of everything that we've done. Like we said earlier, a straight line with a positive gradient represents constant speed. But the constant speed can also be differentiated. That is, if there are more than one object in play, or there is a change in speed, not really necessarily a change in speed. If we want to tell how fast an object is, we can use the stiffness of a line. We can see the green line and the red line, this green line and the red line, this red line. We can see that the green line is faster because it has got more stiffness, and the red line is a little bit slower. That is when compared to the green. Now, when the particle is at rest, it's stationary. We use a straight horizontal line to represent that. Now, when the particle is returning or moving backwards, we use a line with a negative gradient. And when the particle is getting faster, that's the blue line. And getting faster implies acceleration. Is that okay?
Yes, please.
Okay, so that is the summary of the displacement time graph. Let's see what we can do maybe with the velocity. We are not going to keep long. The objective is going to be very simple and short. By the end of the lesson, you should be able to sketch a velocity time graph. Okay, so let's see. Well, this is the question you just answered. How did that? Okay, I think wrong placement of slides. Okay, so just like the others, the distance time graph and the displacement time graph, which runs on the vertical axis. The velocity also runs on the vertical and the time runs on the horizontal.
Mm.
So nothing changes over there. But with this one, the line representation changes a little bit. When it comes to the velocity time graph, a line with positive gradients, a line of this nature represents a constant acceleration. If I'm talking about a constant acceleration, I'm talking about a line with a positive gradient. Okay, so let's say that an object accelerated from rest to a velocity of 3 meters per second. 3 meters per second. So let's say a velocity of 3 meters per second. At this, it maintains, let's say it did this in about 1 second, which is unlikely. Okay, one
Mm.
second. Um, on reaching the 3 meters per second, it's maintained a constant speed. How do you think we're going to represent it?
A straight line at 3 meters. Yeah, like
Okay,
that.
so it's a straight line. That is very good. Okay, so a positive gradient line gives you a constant velocity, and when the particle is moving with a constant speed or constant velocity, we use a line of this nature. Okay,
Yes,
okay. Now, what of a line of this nature? What do you think? A line with a negative gradient,
that would be constant deceleration.
constant deceleration. Oh, okay. I like the way you think it. It's constant deceleration. It's very true. It's constant deceleration. But if you don't take care, this is where people will think that the object is going backwards. You see, for the displacement time graph, a line of that nature represents that implies that the object is going backwards, isn't it?
Mm. Yes.
So if you don't take care, you'll be using that same idea to the velocity time graph. So a line of this nature, instead of seeing this as a constant deceleration, you'll be seeing it as the particle is moving backwards.
Mm.
So if this is not representing the particle moving backwards, what do you think will be the representation when the particle actually starts to move backwards? Because so far, this is what we've got. Let me draw a small sketch. This is what we've got. There's constant acceleration. So CA, this is at rest. Sorry, constant velocity. And this is constant acceleration. Constant acceleration. So when the object is going backwards, what do you think? What do
I
you
think it will go beyond the positive x, like it will go downwards. The line will pass to the negative y-axis side. Oh.
Okay, so let's say that a particle is traveling at a velocity of 5 meters per second backwards. How would you represent this? Is a line you're saying that is going to be at the negative side? It's actually very true, but which shape is the line going to pick? Is it going to pick a shape of this, a shape of this, or a shape of this below the x-axis? So I take the person
Um,
that the particle is traveling with a constant velocity, sorry, not constant velocity, accelerated from rest and attain the velocity of negative 5 meters per second. Which of the lines will this represent?
Wait, can you say the question again? Your line was breaking at the point.
Okay, okay. The particle was accelerating in the
Yeah.
negative direction. Yeah.
Accelerating in the negative direction. That means it will be A.
Oh, okay. That is very good. It's actually A. So let's take this one. So the next slide is going to talk about what I just said. Constant acceleration in opposite direction. So when I'm talking about opposite direction, with this one I'm talking about below the x-axis. I don't know if you can see the white,
Yeah,
this line. Yeah.
yeah, I can see.
So below the x-axis, that is how we represent constant acceleration. So constant acceleration can be represented in two ways. This way, that is if the particle is moving forward, and this way when the particle is moving backwards.
Mm.
Are you getting it?
Yeah, finish.
Okay. So the next one is constant velocity in the opposite direction as well. So in the negative direction, constant velocity won't change. The shape of the curve won't change. It's just the position of the curve is what is going to change. Now, when it comes to the last one, that is constant deceleration. Constant deceleration. So it's a line of this nature. Okay, let me go back 2 slides so that I explain why this line is this way. So acceleration, acceleration causes a change in speed, right?
Yes.
It makes the particle faster. This side is with negative velocity, so negative 3 meters per second. And I think before we started, I was like 5 meters per second and negative 7 meters per second. Which of these two is faster?
Faster, 7.
It's the
Negative
first.
7.
Negative is just for direction.
Yeah.
I get.
Yeah.
So if I'm to find the speed at this point, let's say that the speed at that point is, let's say, negative 2 meters per second. The speed at this point is negative 4 meters per second, and the speed at this point is negative 5 meters per second. You can see that as I move down this line, it's getting faster, right?
Yeah.
So once it's getting faster, we're thinking about acceleration. So that's why the acceleration takes this form, but it's just that it's in the negative direction. The same explanation can go for the positive direction as well. So as you move along the line, you notice that the values at the y-axis keep increasing. So that will tell you that it's moving faster. But the negative over there is just telling you the direction at which this is moving. So it's not as if like it's negative. and we are using the negative value as it is. No, the negative just tells direction. Okay.
Mm-hmm.
And I think with this one again, let's assume that this side is, let's say, 10 meters per second, negative 10 meters per second, of course. So if I move along this line, this definitely won't be greater than 10. It's going to be actually lesser than 10. So let's say negative 8 meters per second. This, if I move along the line, this is going to be, let's say, negative 4 meters per second. And if I move to the final end, this may be negative 2 meters per second. So as you can see, as I'm moving along the line this way, you can see that the speed is actually reducing. The speed is reducing. Are you getting?
Yes, please.
The speed is reducing. So if the speed is reducing, you should know that there is deceleration. There is deceleration. Okay. So that is the main representation when it comes to the um, velocity time graph. Displacement and distance on velocity time graph. Okay. So let's deal with something small. Let's deal with something small. So let's assume that a particle is traveling with a constant velocity, sorry, constant acceleration of 5 meters per second squared. So traveling at a constant acceleration, so constant acceleration of let's say 5 meters per second, and this accelerated from rest, and it took the particle 10 seconds. How would you represent this? I think constant acceleration, there is going to be a steep line, right?
Yeah.
Okay, for 10 seconds. Now, what is the meaning of the line over there? The line, you see, in the displacement time graph,
Yeah.
the gradient of the diagonal line represents which?
Velocity.
Good. It represents velocity. When it comes to the velocity time graph, the gradient represents
Acceleration.
acceleration. Good. So if I tell you that this is accelerating at a rate of 5 meters per second squared, it means that the gradient of this line is 5 meters per second squared. Actually, you don't need the units, it's just 5 units. The gradient is 5.
Mm.
Okay, so with the gradient and the time given, you should be able to find the velocity, can't you?
Yeah.
Okay, so let's find the velocity.
It's 50.
50. The velocity is 50. So ideally, we're saying that the object traveled for um, in 10 seconds. The velocity of the object is what's the name? 50 meters per second. That is
Mm.
good. So let's say that instead of starting from the origin, an object is traveling at a constant speed of 5 meters per second. Constant speed of 5 meters per second. How are we going to represent this one?
Straight line.
Straight line. Good. Um, the object did so in a matter of 20 seconds. So I think this will be the best representation. This will be 20 seconds, right? Assuming
Yeah.
this is a straight line. That's
Yeah.
5 meters. What is the acceleration of this?
0.
Good. The acceleration is 0. There is no stiffness in the line, so the gradient over there is 0. Now, what is the distance covered by the object? So the object is moving with a speed of 5 meters per second. What is the meaning of the 5 meters per second?
That's the velocity. Oh.
The velocity, yes, but what does it mean on
Uh,
displacement?
it means every um every second the particle moves a distance of 5 meters.
Good. So for every second, the distance of the particle increases by 5, or the particle moves 5 meters. Are you getting me? So
Yeah.
if a second, the particle is going to move 5, the second second, 10, the third second, you get what I'm saying and where I'm going, right? So
Yeah.
what is the
Yes.
total distance covered. The total distance covered.
100 meters.
Against 300, right? So it's the
Yes.
same. You can use the this speed is equal to distance times time, right?
Yes.
Speed, sorry, distance over time. Speed is equal to distance over time. Now I can find the distance, which is speed times time, and get that. By looking at this also, you can see the shape. It's more or less like a rectangle, right?
Yes.
The length of this, let's say 20, the breadth is going to be 5. What is the area of this rectangle?
It will be 20 times 5. That's 100.
100 meters. I think that was the same thing you got for the total, what's the name? The total, right?
Yes.
Okay, so we're saying that on the velocity time graph, one, the gradient of the line represents acceleration. Also, the area under the curve represents displacement.
Okay.
So area is equal to displacement. Are you getting me?
Yeah.
The area under the curve represents displacement, and the gradient of the line represents acceleration. Okay. Okay. Can we continue?
Yeah. I'm coming.
Okay.
Okay. I'm done.
Okay. So the main thing over here is that the gradient represents acceleration, and the area under the curve represents the displacement. Okay, so let's summarize everything. On the displacement time graph, velocity is equal to gradient.
Yeah.
When the particle is at rest, we say that the velocity is zero. Is that okay?
Yeah.
On the velocity time graph, acceleration is a positive gradient. Deceleration is with a negative gradient. Is this always the case? On the velocity time graph, is it always the case that the acceleration is with positive gradient?
Okay. No. Unless, because you can sometimes have the acceleration at the negative side. Just that it will be a negative. It will be deceleration in the opposite direction.
I get you. Yes, yes. So this is not always the case. So this summary is actually based on just the top aspect of the graph. I getting it? It's just
Yeah.
the top aspect of the graph. If I go below the x-axis, then what I'm saying is actually very, very false. So with the top aspect of the graph, the acceleration has got a positive gradient and deceleration has got a negative gradient.
Okay. So
Now,
I have a question.
yeah,
So does that mean that for the constant deceleration in the opposite direction, can you call it constant acceleration
constant deceleration
in the opposite direction? Can you call it acceleration?
like this one
Yes,
is still deceleration.
it's still deceleration. So you can't call it acceleration.
No,
Okay.
no, no. It's slow deceleration. And
Okay.
deceleration has got a link to acceleration actually. So if I want to represent deceleration, I can use negatives.
Yes.
So if I want to tell you that a particle is decelerating at a rate of 3 meters per second square, so deceleration is equal to 3 meters per second square. And I don't want to use deceleration, but instead I want to use acceleration, then I say that acceleration is equal to negative 3 meters per second square.
Yes.
Are you getting me?
Yes.
But the raw moment I write deceleration is equal to negative 3 meters per second squared. I'm talking about acceleration. This thing can be a little bit confusing.
Okay.
So an
Using
acceleration,
eh,
yeah.
so using what you just said, that means you can technically say that constant deceleration opposite direction is acceleration. Or
Yes, yes. No, 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 not in opposite direction. Not in opposite direction. Unless we go on the acceleration time graph. This one we are talking about velocity. So the opposite direction over here you're saying is based on the velocity. It's based on unless I'm
Um,
getting your question. Unless maybe I'm not getting your question. But if I'm getting you right, a shape of this nature
yeah,
can't be called a constant acceleration. It's below the x-axis. If
yeah.
it's on top of the x-axis, then it's going to be acceleration. If it's below the x-axis, you can see that the velocity over there is going to be negative and the speed is actually reducing.
Okay,
So
but say let's say we put values in there. Let's say you know your the time it took and the velocity, and you
okay.
use those values like it's being negative and the time positive. That means at the end of the day you get a negative gradient for your line, right?
This one with this line will
Yeah.
give me a positive gradient.
Are you
Or
sure with the negative velocity at that side?
let's find out. Let me clean the screen. Let me clear the screen.
Okay.
Okay. Okay. So let's use values. Let's say this is negative 10 and this is negative 2.
Yeah.
This is obviously 0 and this is let's say
So,
8. How would you find the gradient of the line?
hey God, you people should go. I'll use I can use change in y over change in x, like
What is it?
that. Oh, say I'm coming, please. Hello, say. I'm back.
Yeah.
Sorry.
Okay.
Yeah.
So let's not complicate things. Let's write down the values over it. The x is 8, the y is
Yeah.
negative 2.
Yeah.
At the point, the x is 0, the y is negative 10.
Yes.
Now the gradient of this is going to be equal to change in y, so negative 2 minus negative 10, so it's
Yeah.
plus 10 over 8 minus 0. This is giving you 8 over 8, which is positive.
Oh.
Are you getting me?
Yeah.
So this is going to be, the particle is decelerating at 1 meter per second squared.
Okay.
The particle is decelerating at 1 meter per second squared.
Okay.
Okay. Okay. So constant velocity, acceleration is 0, negative velocity, movement in the opposite direction. Yeah, this is a nice question. Let's see if you can do something about this.
Okay.
Graph description. Oh, okay, let's see if you can describe it.
Find the acceleration between. Okay. The first one is 3 meters per second square.
3 meters per second squared.
Yes.
Okay.
Then the second one is 0.
Mm-hmm.
Then the third one is minus 0.5.
Okay, so what does it mean? The negative
That
0 point.
that
Is the
means
particle
it's,
upwards?
that means what did you say?
What does it mean? Is the particle moving backwards? This is 20, not 40. Okay, this is 20. I don't think we even need it. Yeah.
Okay.
I was asking if the particle was moving backwards.
Um,
Was it moving backwards?
no,
Okay.
it's
What was
not.
it doing?
It's just slowing down.
Good. The particle is slowing down.
Mm,
So it's still moving in the same direction, but just slowing down.
mm.
Is that okay?
Yes, please. Then the next one is negative 2 meters per second square.
Okay. So it slowed down to this side, right? What
Yes.
can you tell me at this side? What can you
At
tell me
this
at
at this
Yeah,
side, it has stopped.
good. The particle has stopped.
Yeah,
Momentarily at rest. Yeah.
yeah. Then this one is 0.5 meters per second.
So after it stopped, what did the particle do?
It's accelerating in the opposite direction.
Yeah, it's accelerating in the opposite direction. And what's the acceleration?
That's 0.5 meters per second.
Meters per second squared.
Yeah.
A
Ah,
second squared.
yes. Yeah.
And the next one,
Yeah. That is it is decelerating in the opposite direction.
so it decelerated to rest.
Yes.
Okay.
And that's 1.05 meters per second square.
Okay. 1.05 meters per second squared. So ideally, if I want to sketch this one, like visualize this. So the particle is moving from this side to this side, constant velocity, keeps going, and it stops and started moving backwards, and it stops. Are you getting it?
Yeah.
So boy, it stops at this point and started moving backwards and stops again.
Mm.
Are you getting it?
Yes, please.
Yeah. So that is just something I'm just bringing out.
Mm. Mm.
Now the person went on to say, find the total distance traveled by the object.
Okay.
So what's the distance for the first 20 seconds of the journey?
That would be 600.
600. Are
Yeah.
you sure?
Yes.
No, I won't. Okay, okay. Yeah. How did you find the 600?
Area of triangle.
Good. The area of the triangle. So half base times height. So this side is 600 meters. The first 20 seconds. Between the 20 seconds and the 40
Um,
seconds.
1,200.
1,200. Okay. Between the 40 and the 80. Which shape is that anyway?
I'll take it as a triangle with a rectangle on top.
That
Hey,
would be
wait.
too. Don't take it as that. That would get you the answer, but that would be too basic. There's a trapezium, and the
Oh,
area of a trapezium is 1/2. The sum of the parallel side. This the parallel side, and
yeah.
this another parallel side. So 60 plus 40, 60 plus 40, 60 plus 40 times the height of the trapezium. In this case, this and this. The distance between this side and this side. Is that okay?
Okay.
So times 40. But what you said is not wrong actually. La, it's too basic. It's tiny actually. So you can take it as trapezium. The area of a trapezium is 1/2 a plus b h, where a plus b, a is the height of the parallel sides. Okay,
Yeah.
okay, good. So do that and get me this
That's 2,400.
2000. And what's of this side? Okay. Hmm. Let's continue.
Okay. Another 400.
Is it the entire thing or
No, just the small. Yeah.
100 to 140? Okay, 400. But why didn't you calculate the entire thing?
Oh. Okay. Yeah, I could have done 200.
You could have calculated for the entire thing. Now, this is the distance traveled. What's the total distance traveled?
That will be 3,000 meters.
How did you get it?
Added everything.
So this plus this plus this plus this plus this plus this.
Yeah.
All the six. You got that one to be 3,000.
Yes.
Okay, okay, okay. 3,000. Are you sure it's 3,000?
Hey, wait. Sorry.
Because this is 2,000, this is 1,200. This and this
So
alone
that's
is 3.
4,800.
Okay, 4,800 meters. So
Meters.
that's a total distance. What of the displacement? What
Um, displacement will be
is it going to be the same 4,800?
no,
Why so?
because it covered a distance with. I'm coming.
Okay.
Okay, because it covered a specific distance, then after that it stopped and went back. So it
Okay. So
undid what it had already done. So it's the displacement is 3,600 meters.
it's 3,600. That's very good. So in other words, in the for displacement on velocity time graph, it's going to be the area above the curve minus the area beneath the curve.
Okay.
So the displacement is going to be above minus below, because the below tells you that the particle is moving backwards, right?
Yes.
Above tells you that the particle is moving forward. So it's going to be the total forward movement minus the backward. So that's why I was trying to sketch this one over here. So the first instance, the particle is moving forward. The last distance, the particle is moving backwards this way. So the displacement is going to be different from the distance. I think we covered this one.
Yeah.
Since the change in direction, the distance and displacement will be different. What of average speed? Do you remember average speed? The total distance over total time taken.
Yeah.
So we'll be able to average velocity, the total velocity, sorry, the total displacement over the total time. Is that okay?
Yes, please.
Good.
So that would
You need
be.
diagram.
Did I?
Draw the diagram.
No.
So how would you revise?
Um. Okay. Yeah, sure. Hmm. 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 Okay. Sure.
Yeah.
Yeah, I've done it.
Okay. Okay. So this is a little bit crazy.
Hmm.
Can you describe the can you describe what is going on in this graph?
Okay. So for the first 20 seconds, the particle moved at a constant velocity.
No, constant acceleration.
Sorry, constant acceleration um let me see, of 3 meters per second square.
Okay.
Then it moved at a constant velocity or constant velocity of 60 meters per second for 20 seconds.
Okay.
Yes. Then for 40 seconds it decelerated.
At a constant rate.
Yes, at a constant rate of.
Let's leave the calculation out.
Okay.
Let's leave the calculation out.
Okay.
I just want you to be sure of what is going on with the graph. Are you
Okay.
getting me?
Yes,
T
please.
constant. acceleration. You should know partial acceleration. Okay, what of the next part from 80? How would you explain that jump?
Okay. Mm. Okay. At 80, it it came to a rapid stop. Or yeah.
Yeah, momentarily at rest. Yeah, at that moment it came it came to rest and change direction.
Mm.
Like a swift change of direction. So let's see if I'm to sketch this one. Let's say from this side to this side, the particle was moving forward. At this side, there was a swift change of direction and it started going backwards.
Mm.
Right,
Accelerating the opposite direction.
accelerating in the opposite direction.
Yeah.
Then what else?
Then between then after that, it decelerated in the opposite direction for 40 seconds.
Okay.
So it came to a rest.
Mm-hmm.
Then for 20 seconds, it accelerated
And is it
constantly
where in which direction? Is it to the left or to the right? Based on what I'm doing, is it to the left or to the right?
to the right.
The right. Good.
Yeah.
Good. So if you are able to describe all this, it will be very difficult for any examiner to trick you because this question is a little bit tricky. Okay, now if I tell you to find the total displacement, you should be able to do that for me, can't
Yeah.
you?
Yes.
You've done well. You've done well. So time with you is up. Later we discuss these questions. Okay.
Okay. Okay.
So that is all for today's class. Take good care of yourself, and we're going to meet on Saturday.
Okay.
Bye bye.
Yeah.